Molecular model kits that we don't get to use this year. I'm really sorry because they're fun. Once you're done making the molecules, you can make little dogs and seals and all kinds of things with them. But we can't do that this year. What we're going to talk about today is something called valence shell electron pair repulsion theory. That's right, valence shell electron pair repulsion theory, otherwise abbreviated VSEPR, because nobody in their right mind wants to write that out loud. Now, that actually means something if you think about it. What electrons do the bonding? Well, those would be the valence electrons, the ones in the valence shell. They do the bonding. What do electron pairs do? Well, like charges repel. So what this is telling you is the bonding electrons will repel each other, and that is going to give us some information. And what we need to do to use valence shell electron pair repulsion theory, or VSEPR theory, is to know how lone pairs and how bonding pairs are going to react. So this is all based on electron repulsion. Because they have like charges, electrons will repel each other. So let's take a hypothetical compound XAA. And let's not worry about completing the octet rule for A. We can pretend it's hydrogen. We don't have to. We have two bonding pairs between X and A, and we have two lone pairs. In order to do their job of being bonding pairs, the electrons between X and A are constrained to a certain area of space. These electron pairs are stuck between X and A forever. They cannot wander down to Starbucks and get a cup of coffee. They're just stuck there. They don't take up very much room because, if they wandered away, again, they wouldn't be doing their job. The lone pairs, however, have nothing holding the other ends of them down. So the lone pairs take up considerably more space. The space taken up by the lone pairs results in a greater repulsion for two lone pairs for each other, whereas the repulsion between bonding pairs is quite small because they do not take up a lot of space. Now, when we get back into the classroom, into meet, I've got a good analogy to tell you about people and airline seats, but it's no fun unless I can use my hands, so we're not going to do that now. Let's just rank these electron pair repulsions, largest to smallest. Okay, the largest electron pair repulsions are between two lone pairs. And I'm just going to do LP and LP for lone pairs because it's a lot shorter to write. Those are the largest. In between are the repulsions between the lone pairs, or any lone pair, and a bonding pair. And the smallest repulsions of all are between two bonding pairs. Now, the fact that there are repulsions at all, and that they are different in size depending on what the job of the electron is, or the electron pair is, will let you go from a Lewis dot structure, which is correct. You got to have the right ones, which is why we corrected them 2 days ago, to a three-dimensional geometry. So instead of showing water, that's not water. Instead of showing water like that, we can show water in 3 dimensions. Well, water is pretty two-dimensional anyway. But say NH3. Okay, NH3, we kind of draw like this on a piece of paper, just a messy triangle, but it actually has some depth to it. It's a little pyramid. Okay, and there's about 120 degrees in between here, but actually a little less than that. And CH4, which we always write as a square, or as a cross, actually looks like this. So that's what we're going to do next time, is figure out how we get these shapes from Lewis dot structures. Okay.